We can express the average rate of change of a function over an interval in multiple ways. So using the rise over run in this first case, the rise would be f of a plus h minus f of a over the run, which is a plus h minus a. And in this second case, the rise would be f of x minus f of a over x minus a. So these are the slopes of the secant line. And from the average rate of change, we can obtain the instantaneous rate of change at x equals a by taking the limit as h approaches 0. So as h gets smaller and smaller, we get a better approximation to the slope of the tangent to the curve at a. And basically the tangent touches the curve only once at a. And similarly for this second case, if we take the limit as x approaches a, then in a similar way we get a better approximation to the slope of the tangent to the curve at a. And that's provided that these limits exist. So these two are equivalent forms of the derivative evaluated at a, which we denote f dash of a. Let's do a more formal definition of the derivative. So what we do first is take the average rate of change between 2 points, or the slope of the secant line. So that will be the rise on the run, which is x plus h minus x. And then if we take the limit as h approaches 0, we obtain the slope of the tangent to the curve at x. So for example, as h gets smaller and smaller, we get another secant, and that gives a better approximation to the slope of the tangent to the curve at x. And this tangent touches the curve only at x. Okay, so this slope of the tangent line is the derivative, which is denoted f dash of x, provided that this limit exists. So other notations you may see for the derivative is dy dx, y dash of x, and so on. Let's evaluate this derivative using the definition. So we have the limit as h approaches 0, and our function is root x, so that will be root x plus h minus root x over h. And we multiply this by the conjugate in the numerator and denominator. So that will be root x plus h by root x plus h, then minus root x by root x over h, multiplied by the square root of x plus h plus root x. And now we can see that x is going to cancel, and h is going to cancel, so we get 1 in the numerator, and this limit thereby evaluates to 1 over 2 root x when h approaches 0. We can represent the derivative in a number of ways. So here we represent it graphically as a slope of the tangent line to the parabolic curve at x equals 2. So you can approximate the derivative by obtaining a slope of this tangent line. So if we choose 2 points, we can obtain the rise over the run. So that will be 16 minus 4 over 5 minus 2. Now we can also approximate the derivative numerically. So here we have the function evaluated for several x values. So again we can approximate the derivative at x equals 2 using the rise over the run. So it'll be 9 minus 4 on 3 minus 2, which in this case gives a slope of 5. So in this case we've chosen x equals 2 and x equals 3. So it's going to give a steeper slope compared to the actual tangent line at x equals 2. Now we can also represent the derivative analytically. So here you could use the definition of the derivative. So we take the limit as h approaches 0. And then using our function, we can obtain the slope of the secant line. And if you evaluate this limit, you'll obtain this result. And we can also represent the derivative verbally as the instantaneous rate of change of a function y with respect to the independent variable x at a particular point. So for example, at x equals 2, we'd have dy dx evaluated at 2, or f dash of 2, and so on. Let's estimate the derivative graphically and using the information from this table. So we suppose that we want the derivative at x equals 3. So we draw a tangent line that only touches this point on the curve as best as we can. And now we can find the slope of this tangent line. So using the point at x equals 4 and the point at x equals 3, we have the rise, which is 15 minus 9, on the run, which is 4 minus 3. And similarly, if we want f dash of 3 using the table, well, what we need to do is choose the x values that are closest to 3. So the rise would be 16 minus 4 on the run, which is 4 minus 2. And that gives us the same result. And this happens to be the exact value of the derivative of this function at x equals 3. And sometimes you can get the exact value for simple curves like this. Let's use technology to estimate the derivative of a function at a point. So we did this previously by drawing the tangent line manually. So let's first plot our curve. And now to approximate the derivative, we can use second function, calculate, and choose option 6. And now we can enter an x value of 3, because we want the derivative at x equals 3. And that gives us dy dx is equal to 6, which is the same result that we've obtained using the graphical method here.